Bourbin. I've been in the club for a while now. My handle is Selvis on the forums, and what I'm going to be talking about today is basically connections inside your Droid, how to communicate the different systems, and I'm going to go into some introduction. So here's what I'm doing. My agenda is I'm going to give an introduction about myself and what I'm going to be talking about. I'm going to talk about something you've seen my presentations in the past, what I call toolbox moments. I'm going to give some basics on communication, talk about some protocols, and then how I've implemented them, what I've used them for, and then touch on some future stuff, and then I'll summarize it all. I'll leave time at the end for any questions. So if you have anything, let's just hold it to the end. Let's take it from there. So basically, who am I? I know some of the people in this room, some people may not know me. So I'll give you a little introduction. I've been dabbling in electronics for a long time. I worked at a company called Catapult back in the early 90s. We made one of the first online systems for video games. For Nintendo, Super Nintendo, and the Genesis, and we had a special cartridge, and I worked on hardware and software for that thing. And this is what that machine looked like. Then for the last 17 years, I've been in the video game industry for 30 years. The last 17 I've been at Electronic Arts. That's where I am now, where I've been working on high-performance game engines. So I'm a software engineer at heart, and I dabbled in electronics, and that has shifted over the years. And what people in the club kind of know me for is I make these little blinky lights, or at least I used to. And I have like 1,000 different versions of them out there. And the whole point of what I do is I try to make things that people find useful and then share knowledge so everyone can do this kind of stuff themselves, even if you don't have the background. I think that's what's great about this club. We have a wide variety of experiences and expertise, and we have a way of sharing it all. So that's me. What I'm going to be talking about today is specifically around communication. So along the way, I'm going to be mentioning these things called toolbox moments. Now what these are little things that when I'm developing or working on systems, aha moments. Something which I learned, and then I take that and I put it in my toolbox for later. Now, I'm going to say some things, and you may agree with them or disagree, and that's fine. These work for me. So I just want to share them with other people. Now for some of the basics. Since we're talking about communication, we're going to be talking about microcontrollers, because that's what pretty much most people use in their droids. And then how do they communicate with each other? You may have multiple things. You may have sensors. You may have multiple processors, all that kind of stuff. How do they talk to each other? So one of the concepts you're going to be using, and by the way, I'm going to be talking about some low-level details. There's a lot of abstractions that you don't really need to know a lot of what I'm talking about, but I find it interesting to at least know the basics. And then when something goes wrong, you know kind of where to look. But there's these things called UARTs, and these are universal asynchronous receiver transmitters. Think about it as a part of a microprocessor that takes care of the nitty-gritty details so that you don't have to. So these things handle a lot of the specifics around communication, and I'm going to go into a little more about baud rate, parity, start and stop bits. But one of the things I want to say on this slide is, and I have kind of a picture of two different microprocessors. These are the ones which I use in most of my designs. The Atmel, so you can think of these as Arduino. They are but there's these self-contained little microprocessors. I use those a lot of the time, and then I've switched over to the ST Micro. Think about it as ARM chips, think about it as like your cell phone. So those are two of the predominant types of architectures. They all have these UARTs in them. The difference is going to be how many of them and how easy are they to be used. I mentioned the general purpose I/O pins here, because all these processors have a lot of pins coming off of them, and they're different numbers. And they're going to have different numbers of these UARTs. To utilize everything, there's some constraints you have. So there's certain microprocessors, there's going to be only a number of UARTs you can use, and you're going to explicitly have to use certain pins. These are all intricate details, but it just means that you have to know something about your processor to be able to get the most out of it. And then the last thing on this slide we're talking about is interrupts. When you're doing communication, there's information flowing over these wires, and you need to take them and put them somewhere, and you need to do that a lot of times if you're running other things, other software at the same time. So think about it as asynchronous stuff. So you need a way of doing that, but you don't want to stall anything else out. So a lot of how this communication works is there's interrupts that are set up so that when some byte arrives, interrupt triggers, so you can take that thing off the bus, on the FIFO, so that it can be used later. And the main thing I want to talk about interrupts is when you're working with these, the rule of thumb is you want to get in and get out really, really quickly. So the longer you're in an interrupt, they block, and it means other things can't happen. So when you're doing communication, and again, if you're using like Arduino setups, you can have libraries, and they're going to have all the details of these things. But you want to do that really quickly. That's what I would say about it. So some of the basics, right? I talked about zero frame. When I said baud rate, basically it's an agreed upon frequency that things are going to talk to each other. And I'm going to go into some protocols and we'll go into some more details, but the idea is this is the speed of the transfer. Think about that as the baud rate. When you hear the word parity, it's just about error detection. It's a way of summing up bits so that you know it's even or odd, and that's just one way of making communications more reliable. And then there's this other thing called start and stop bits. So one thing I wanted to mention here is when you're communicating, you have a payload, you have data that you're sending back and forth. But then there's also this overhead, this other stuff, which is, if you got bandwidth, it's also stuff that can be transferred. These start and stop bits are a way of defining, what's a packet, what's a narrative. And these different protocols are going to handle this stuff differently. But when we talk about it, that's it's the stuff around your data. So that's some of the basics. Now, for some of the protocols and things that we use inside these droids, the first one I want to talk about is I2C or I2C. It's integrated circuit. It's a way of communicating from one device to another. This is made really for short distances. So we'll talk about these different protocols and their pros and cons. This is short distances. It requires two wires. There's clock and theta and clock. So it's a synchronous communication. There's no start and stop bits, and that's not exactly true. There's an acknowledgement at the end, so you can think about it as a stop bit. But again, remember I talked about there's this bandwidth. There's your payload and then overhead. This has less overhead because you don't have some of that stuff. There's really two speeds this can go at. There's a fast one, which is 400k hertz. And then there's, I think it's standard, called slow, but 100k. There's also some advanced additional things that we go faster, but this is like the standard I2C. I2C works with what's called addressing. So like each item that is on the bus has an address. And this address could be 7 bits or 10 bits, but it has to be unique. And this is how you communicate. When you do this type of communication, you basically say, I want to talk to this thing, my address, and then you send data. Then there's SPI interface, or the serial peripheral interface. This also is for short distances, but it's 4 wires. And the reason for that is this is now a full duplex type of protocol where you can transmit and receive at the same time because you have more lines to do that. The model here is you have a controller, and then you have multiple peripherals. So one of those lines is this chip select, or a select bit, where you basically raise the line of, okay, this is who I want to talk to, and then the controller can talk to that peripheral. And so you can have lots of these peripherals. These 2 protocols you can find are standards. There are things out in the wild. If you buy, a sensor or stuff, it's going to talk to one of these things. So it's really easy to interface with. And they will have some constant address, like I2C. Then we have serial. So there's a standard, the RS-232. This thing is for longer distances. There's 2 wires here. There's a transmit and receive, but it's asynchronous. So you notice that there really isn't a clock here. There's an implied clock because this has fixed baud rates. The difference here is, the transmitter and receiver have to agree upon what's that speed, what's that baud rate. Where those other protocols, you can kind of do things like stretching clocks. So you have a lot more flexibility and you can be dynamic. Serial is not that way. It's more of you agree upon something and then you communicate. This is where the UARTs really come into play because they handle some of the intricacies of that communication. There's some other stuff. There's flow control in serial, but I'm not going to really talk about that. I don't think many people use that anymore. It was back in the old days when we had terminals and they needed this kind of flow control. But just think about it as 2 wires, transmit and receive. Then I'm going to talk about something called DMX. This is kind of the big part of what, when I talk about my implementation, I'm going to go into more details. But this is a digital multiplex protocol. I believe it came around originally for like dimmer switches, like lighting dimmer switches. And it's a way of sending information to these different controls. There's a standard around this, it's the RS-485. What's the wires here are D plus and D minus. It's a differential signal. The reason for this is they want low noise here. And so the protocol is doing things to make that possible and get much longer distances. I'm going to go into more details there. But they use something called this model of a universe controller model. So a universe is 512 bytes of data. And I'm going to interchange here data and channels because DMX, I wanted to have a visual aid. So this is a DMX board which I made. I'm going to talk more about it, but for this part, I just wanted to point out these are all the dip switches up here where we set an address for this particular board. And the way DMX works is that every board has its own address. Think of address as offset into this 512 bytes of data. Like where does your data start? And then you use a block of it, and someone else can have a different address, and they use a different block. or you can have two of these things and they live in different spaces. But each board will have its own address. And like with Minecraft, you can set that for each board. And that's just the way the protocol works. So it's a starting position and then you have data.
Question. From the physical connections aspect, the first two you described were like shared wires on a box, right? Serial point to point. DMX looks like it's kind of, it's like a daisy chain almost, is that correct?
So I'll go into
Okay,
more.
my other piece of the question is, 512 bytes or bits of data?
That's 512 bytes of data. So, I don't know what to bring. So first, I mentioned differential signal. So this is the difference between D plus, the data plus and data minus. And this is what gives us the 1,000 feet distance. I mentioned that this is for, started out for lighting controllers. Where it's being used now and why I'm even talking to you about it is it's using stages and performances. And here's where I have to be a little careful, so I'm going to talk hypothetically about some stuff. We mentioned, Lucasfilm yesterday, there's a bunch of things that they do, and our droids get used and stuff we can talk about and not. Lucasfilm is part of a bigger organization, and that bigger organization also does things with droids. And there could be setups on stages where they need to control stuff, and where DMX is a perfect fit. And so, that's how it kind of ties into R2s. And I'll talk about some implementation details later. Yes?
So, being a stagehand, we do use DMX. So, do you prefer the 5-pin or you can send DMX signals through a 3-pin configuration as well?
Yeah. So I'll talk about that in my implementation. But essentially, 3 versus 5 is you have a second channel. There's a primary channel and a secondary channel. Mm-hmm. And so it's slightly different. Again, be careful. What I was working with had this as a standard, and so when I did my stuff, it was dictated around what kind of connection would be going. But all you need is 3 pins to talk DMX. You don't need the 5 pins. I will say right now, I'm not a DMX expert. I know as much to be dangerous. But there's probably specific reasons for that second channel.
Yeah, it's used for so you can send packets back and forth between different moving lights and different LED lights a little bit quicker. But that was the limitations of DMX. So
there you have it. Yeah, I'm more expert. And so the packets, just want to give some specifics. 256K is bits, not bytes. And there's no parity, but there are stop bits. And so the format of the frame, I'm not going to really go into a lot of detail here, but to know if there's a very specific frame here. And what DMX does is, remember I said there's 512 bytes of data, and each one of those is a channel. And I'm going to talk about some implementation details later. But it transmits all of that stuff every frame. I think it's 23 milliseconds is for each of these frames of data. So that's how much information is being sent all the time. And the individual devices is going to be looking at their channels of information, and there's embedded information there to say, at least the stuff I work on, is any of this stuff needed for this frame? Because you can have no stuff in there, like, for this frame, I'm not going to do anything. Just what I said before, and there's nothing new to do. But the way to look at this is like a sequencer. This is a script that they want these devices to do, and it's a repeatable script. Again, think of stage, think of a show, and think of stuff they want to happen the same way every time they do it. This is a way of implementing that in electronics. And so, again, I'm not going to go into some of the details of this slide, but there are some important information here where some of the stuff is variable. So, like, you can delay a period of time, and that's perfectly okay. That's actually, required on stuff. So the protocol handles that. And let's bring me to my first toolbox moment. I talked a lot about standards, talked a lot about things that exist, and my toolbox moment here is if you're going to reinvent the wheel, make sure there's a good reason to do so. The flip side of that is you have these things, use them. They use, like if you looked at my Droid and said, well, why would you even need to use that? Well, it's standard. There's lots of stuff that works with them. I test myself out with a DMX controller, which I bought on, eBay. It's a standardized thing, but it's taught all the stuff I'm working on. So I'm using standard here. So now I'm going to get into some implementation details. And again, I'll be careful what I say, so I don't say anything I'm not supposed to. But this is how I use it. So first, I'm going to talk about connections. So this is where I started. These 0.1-inch headers. We have connectors, and this is how things were linked up into my Droid. And when talking to client and doing things that will be used in production environments, this is not good enough. This is not where you should be going. What we use is RJ45. This is an 8-pin connector. Think about it as Ethernet. Think about those things. Reliability is going to be a word you're going to hear a lot from me. So you want different kinds of connectors that give you reliability. I use two main types, RJ45 and RJ12. The difference here is the number of pins and some stuff like that. But the main point here is the connector. How reliable is this? And then we have, sorry.
So RJ45, because I know when you do that, you have like the splits and stuff like that. You have to do like, is that okay to deal with that?
You want to use that.
You want,
Yes.
I didn't know if there was something you would need to do. You use the same connector, but the wire has to.
Yeah. Actually, a lot of the stuff is the same in there. And then for the DMX, again, by implementation, you'll see these different connectors on here. These are RJ45s, RJ12s, and then you have these XLR connectors. And the thing that you know about them, is they're very reliable connections.
Good.
That is a big thing in dealing with this kind of stuff with this supply. I'm showing the 5-pin here. Think the same thing with the 3-pin, just more pins. So the next toolbox moment, thing that I put in my toolbox is think long-term and reliable and not least resistant easy path. It is really easy to use those headers, and all of our stuff has that stuff on there. And we're just, we're not even thinking about it. But there are other people who are. So, and it's not really a big change in cost to you, or effort, or space even. It's a little bit bigger, but the benefits totally outweigh that. The other thing which I'll mention when thinking about reliability is, okay, what if this board gets wet? What do you do then? So when building stuff for this client in this type of environment, you're also thinking about those types of stuff. There are ways of coding these boards so that they are more reliable. So when looking at electronics, and again, that's my background in this club, that's kind of what I do, the stuff which I make takes those things into account. So more into implementation details. Some people will remember this slide from one of my previous presentations. This is by PSI block architecture. And the thing I wanted to point out here is, on this left-hand side, there's an I2C connection coming in there. There's a serial connection coming in there. When I build my implementations, I try to do things agnostic, so that I have the choice of what I want to use. So I'll put in the capabilities, but I've been thinking about this from very early on. And then this goes to some of my implementations. I have I2C buses on my original PSI boards. When I went to making things more configurable and having controllers, I've used SPI interfaces to connect things up, and then more of the same when talking with this. I use OLED displays for some information, and I talk SPI interface. So I've been using these in a lot of the boards that you've been buying from me over the years. You just didn't know it. And then that brings me to this hypothetical implementation of a system, which is an integrated system, and the way I designed this, so this is the DMX board, and kind of think of this as a hub. And there's DMX protocol coming into this from a big controller board. You can probably see them on shows where you have all these knobs and sliders and stuff, like that. And so that's the input. And then what I do is I take all that stuff, and on all of these connections is going out to a different peripheral inside the Droid that talks a serial protocol. So I'm taking DMX in and talking serial to all my devices inside the Droid. And since I control this whole environment, the baud rate thing it's not a problem because I control everything. I know the distances, so it doesn't, get in my way. So as I talked about RJ45s, RJ12s, my system handles all the link-like type stuff. So I made PSIs that talk this protocol. I've made HPs that talk this protocol. Someone else in this room makes Logics and is able to talk the same protocol, and it's in probably a lot of people's droids. It's the best logic system, that's ever been made. I don't think I'm building it up too much, but it also works with the system. And the idea of what I implemented is a single power source in the droid. And if you heard my presentations in the past, I like to have on each board a regulator. So like the board has what, a voltage that it wants to use, but I don't like to dictate, okay, well, what should the system be? And so it's able to take in anything that our droids do and bump it down to what, that board needs to do. But in this implementation, there is one power source that feeds this, and then this feeds everything else. And then this is an eye chart. But what I wanted to show here is this is my protocol. And I say my, but again, don't reinvent the wheel if you don't need to. Leverage off of what people have done before. This uses the Jedi serial protocol. So the Jawa light, that's what it's called. What I did is I took that and then I added things onto there. So like my stuff talks that exact same protocol. It adds some additional commands, and it's all standard. So like anything that worked with its old boards will work with this, plus there's additional stuff. And when I do my protocol, I've added things. We have RGB lights and everything now. So like everyone talks in RGB, but there are clients that don't talk that color space. They work in a different color space, HSD. And my boards will take either one of them, and it does conversion fees between them. So the point here is extensibility, flexibility, and you don't have to lock into one of them. And so it brings me to another toolbox moment of build for testing and validation all along the way. So one of the main reasons why I chose to leverage the standard here is it's serial, and I didn't really point it out in the last part, but it's ASCII, so it's you can see it on a terminal. You send serial, you know, it's a byte, and it's really great for debugging. So this validation of when I'm running a system, I write things in blocks and get things working at a block level, like keep on expanding. But I can validate things all along the way. This interface allows me to do it with ASCII strings and sending that kind of information. So this really works in your favor. And then this is the DMX side of it. So remember I said there's 512 bytes. This is based upon, for my client, what they needed to be able to control. So this is defined by us for their use case and the kinds of data. And so there are, in my DMX packet, you know, the thing I own, my channels, has HP information, it has PSI information, it has logics, we do logics information, and then this board takes that and sends it to each one of the different devices, and then they do their thing. They all have their own firmware, but this is the definition, this is the source of truth for the stage. And it brings me to, I think this is one of my last toolbox moments, which is, this is, again, you may agree or disagree, but what I go by is keep the hardware simple, solve the software. So what I mean there is it takes a lot more to rev hardware. So get a base level working in hardware and then iterate more in software. And only iterate in hardware when you have to. You can't do it in software anymore. This is the big thing when I worked at Catapult, working at the X-band modem, is the lead times were a lot greater than they are today. And so like we had to rep a board, that was significant. But we can do magic in software. We can fix problems in hardware and software. So that is, one of the things I'm going to park onto you or not. And then from a software standpoint, keep the software modular built-in blocks. So that's, I've been working in software for many, many years. I like to work in modules and build up libraries of stuff and use libraries of stuff. Don't reinvent the wheel unless you need to. This all feeds into that. And then you can layer software. Which now brings us to the future. So I talked a lot about DMX and these controllers, these big wires that connect things. But we have droids that work out in the world using remote controls. There's no big wire attached to it. It's not tethered. So it seems to be a disconnect here. I'm talking about something that doesn't really relate to you. But this is kind of my future part is, okay, think of that DMX wire that was connecting to a big board, and like interject here some kind of wireless thing. And so now you have your droid, which is not tethered, but still utilizes all of this stuff. So this is where I'm going, my next step. This wasn't necessary for my client. This is, I'm looking at the builder's club. This is what And so to summarize all of this, multiple ways to connect things to your Droid. Serial communications, hopefully you see it's really not hard. There's lots of software that takes care of the nitty-gritties. There's hardware that takes care of the intricacies of communication, and it's just a few wires. So this is not rocket science. Think about reliability in your implementations. Think about it from the beginning. They're harder to add on at the end. So when you're designing stuff, you know, I would recommend this in one of your requirements. And then leverage standards and build upon what others have done. It's only going to help you in the end. And again, that's what we are. We're a club. We leverage each other. We make things even better by having that base knowledge. And the last thing is I can do a presentation, on something other than PSIs, but I have to add sort of, and I did PSIs on something. But that's it. Are there any questions? Yeah. So it's interesting. The answer to the question is yes, because. Remember what I said about the address is kind of like a base offset to data? So you could have multiple boards looking at that same data, maybe they interpret it different. So then you could be at the same address. But the way to think about it is, that's telling me data which I want to read. Is that unique to my controller, or is that unique to multiple controllers? So the answer is, the option is yours.
So the board you currently have that controls PSIs. I'm kind of a noob, I get it. But what I was curious, can those control servos?
So they could. My implementation didn't need to, but that is definitely a future next step thing.
So future possibility that I could pretty much control my Droid with my lighting console that I have in my theater.
Yes, that is the goal.
Okay, you are making me very happy right now.
My job is done. Thank you very much. Yes.
So, this is where we have one of this. Is there any feedback between the client and the master, or is it all just broadcast?
It's broadcast, but like we were mentioning, there's another channel. My implementation doesn't use that, but the capability is there. And what I would say is, there are some future things that, I'm honestly looking at. I'm looking at a second channel for other possibilities, but there's nothing that stops that. Yeah. There's a primary and secondary. That's what they call it. Again, I'm not a DNX expert, but that's how I am.
I noticed that's a really robust connection connector. How does that play mechanically with thermal stability on the circuit board? If you put that into a front panel, or is what?
So that's a good question, because this is just the tip of the spear. There's a whole bunch of things. So being careful what I talk about. My world is a subset. There's a bigger world where the concepts I'm talking about, they also take into account. And one thing I didn't mention is what my talk is going to be about is think about it as the brain and nervous system of the droid. But there are people who work on the body, the skeleton, but they use the same kind of concepts that obviously. So the answer is yes. They also factor that in to how is this board mounted? Where is it mounted? What's actually accessible to it? Because again, we're talking about stage, and we're talking about, there are people who are not going to understand the intricacies of this, but they know their world. And especially in stage performances where it happens over and over and over again, and it, you know, it needs to go off like clockwork. So they factor that into the mechanical design of things. Okay. Thank you very much.